All right, welcome to our Kubernetes for Developers lightning lesson. So just a quick view into what to expect from Kubernetes as a developer or from the point of view of developers. And we're going to go through six kind of different points that might be of interest for a developer. We're going to start off with a quick intro into Kubernetes in general, and then talk about these six different parts. Starting off with containerization, then designing your software for containers, Kubernetes a way of abstracting resource access, and then a little bit about security on Kubernetes, a little bit about networking, and then finally, kind of the trouble that we get into when we want to do debugging and troubleshooting in Kubernetes. Starting off with Kubernetes in general, I think everybody knows already that it comes from Google originally. So Google containerized their workloads originally, and then they needed to have this kind of management layer that would take care of the containers, make it possible for automatic scaling of the containers, taking care of networking between the containers, security, of course, as well. And this system was called Borg originally with Google, and they had this kind of limitation or design goal of running a maximum of 10,000 pods on the same cluster, right? So that's kind of the scale of the operation that was running. So no, it was not one system for the whole Google environment, but rather they partitioned their kind of servers into these roughly 10,000 pod-sized partitions. Starting off with containerization. So let's say that we're a developer and we haven't really used containers before. That is a prerequisite for using containers, for using Kubernetes, because Kubernetes is a container management system. And we are generally speaking about two different use cases. So either we have an existing application, and then we want to move it into a container, or then we're creating a totally new application. And more about that in a bit. But yeah, moving an existing application into a container sounds simple. I can already, hear in my mind a project manager telling a developer, just stick it into a container and then we run it on Kubernetes, and that's going to solve everything. But the reality is a little bit more complicated. We're finding the correct base images for the containers that have the right amount of dependencies on them, but nothing extra, is surprisingly time consuming. And what we see very often due to that are containers that kind of have, pretty much a whole Linux distribution on them. And due to that, they are huge in size. And then, that's not very nice. They take up lots of resources, lots of disk space, takes a long time to download, and so on. So kind of from that point of view, moving existing application into container sounds simple, but we can find quite a lot of trouble even in such a simple use case as well. Well, then you'd say, well, creating a new application, that needs to be simple then, right? Because then you literally need only the stuff that there's kind of no legacy. There are no legacy dependencies, right? It's just kind of, we only need the stuff that we actually going to use. But even in that case, this can be complicated, right? If we are talking about something like a Python application, then what kind of build process are we going to work with? Where do we start off with? Do we start off with an official Python base image, and then we run pip on it to download the dependencies that our code requires? Or are we talking about a different kind of environment, maybe something in Go or in Java, or we actually need to compile something first, right? So just Java as an example. We have something that has Java tools on it, the JDK, Java compiler. But then we also need something like Maven to control the dependencies again. For tests, we want to have JUnit available. But then we don't want to have that in the deployment environment. We don't do anything with unit testing frameworks over there. So containerization itself is already difficult, right? It gives us a standardized, repeatable artifact that we can move between different environments, literally run it on our laptop, and then in the production environment, and it should run the same, almost the same at least. But to get there, to kind of get that benefit of portability, there's quite a lot of work that needs to be done. And again, there are many possibilities to take unnecessary technical debt here by making taking shortcuts when deciding on your container image definition. Well, onwards to our second topic. It's going to be designing for containers, right? So the containerization allows us to do different kinds of design decisions. So this most likely requires reworking of the original software if the original software was a normal monolith. But we have the possibility to use different kinds of patterns for distributed systems to work in a containerized environment. And what does that give us? So this idea of decoupling direct dependencies allows us then to individually deploy and scale the different parts, the different, let's say, couples of the software. There are many different kinds of patterns that allow us to do this. In the container world, just even a simple sidecar pattern is something that we don't really see in traditional software development. A sidecar is a second container that's always deployed together with the application container that can then maybe contain some reusable stuff like a log consolidating software or maybe a application mesh implementation for networking. That's kind of one of the patterns that is kind of new if you're going towards containers. There are also other kind of patterns that have more to do with microservices architectures, especially if we are moving from monoliths to microservices using something like the Strangler Fig pattern. Then we have to do kind of mock interfaces, kind of mocking the old way that the software used to work, and then allowing us to actually rewrite a software in a kind of more microservice-oriented way. Could be different kinds of proxy or other kinds of patterns that we would use for that. Making it possible to have the same backend functionality work through two different ways, two different APIs simultaneously. So a lot to learn over there, and not everything will happen overnight. Rather, we really have to try different things out and see how the different patterns allow us to work through different kinds of problems that a distributed system then presents us. Well, next time we're going to go on more towards Kubernetes. Though previously was just kind of generic container stuff. If you're in a traditional environment where might be used to accessing resources quite directly. Like if we want to write something to a disk, then we just do it. We have a file somewhere in a directory somewhere, and we just read it or write it. But in Kubernetes, when we're deploying pods onto various machines, then how can we ensure that those pods will somehow have some disk, either some space somewhere to be able to write to, or can we even make sure that there is going to be a disk that's going to be mounted into the file system and that we can read from, right? So that kind of disk a model is called a volume in Kubernetes. There are multiple different types of volumes that we can use, starting off with something like an empty dir volume, which is just a memory-backed, basically a RAM disk directory in the container's file system that we can use for I don't know, caching, or file something that we can download some files to before we need to work with them. And that volume, for example, that will be wiped as soon as the pod is destroyed, right? So there's no persistence in there. There's persistent volumes are separate in Kubernetes, which can then be backed with different technologies. So for example, in the cloud, those persistent volumes could be backed by virtual disks, like EBS on AWS, virtual disks on Azure. Similarly, we could also back that by something like an NFS share, a network file system, which then again can be modeled by different kind of cloud products. One very specific storage resource in Kubernetes is a config map. A config map is basically a set of keys and values, something that we very often use for configuration. And one of the best practices of 12-factor is this idea of the code path being equal in all environments, from development through testing all the way to production. But how can we do that if we, for example, access different databases in the test and production environments? Well, by changing the config maps, right? So the config map object itself is going to be different depending on the environment. But our software is going to read the same keys from the config, and then we'll connect to different databases because the values are going to be different. Config maps in Kubernetes are saved in the central database of Kubernetes called etcd. And thus, whenever our pod gets deployed somewhere, the config map that it is referring to can then be mounted as a kind of a virtual file system on the container. And then we can just read from that file system, or we can also use the keys and values as environment variables in the environment. That's another possibility. One special kind of config map is something called a secret. Secrets are saved as or shown as base64 encoded strings. And in many Kubernetes environments, the secrets are encrypted when written to disk. However, in memory, they are still totally unencrypted and readable. Secrets could be things like usernames and passwords for database connections or API keys or that kind of stuff that we kind of want to use extra care with. And in Kubernetes, it's nowadays best practice to mount these secrets as file systems as well, instead of using environment variables. Well, when we're talking about secrets, then an interesting thing could be security. So how does security work in Kubernetes? So the Kubernetes API server is protected, and we can have different kinds of identities that our people can declare. So we have users. Users are like maybe operators or maybe even developers on a cluster. We can also have groups. So it's easier to give permissions to multiple users simultaneously. And then finally, we also have an identity called a service account. And the service account is a user that belongs to an application, basically. So we say that this application has this identity. From an authorization point of view, the security system that Kubernetes uses is a role-based access control, so RBAC. What that means is that we create roles. Roles are a combination of resources and actions. So we could say like get the status of a pod in Kubernetes. That will be a role. And of course, we can have multiple of these in the same role. So we could have something like a secrets reader who can read secrets, or config map reader, something like that. Okay. So with that role, what we do with that role is we bind that role to an identity using a role binding. That means that multiple identities can use the same role. So the roles themselves are reusable. And remember, one of those identities could be an application. So how does that work? Well, when we are creating a Kubernetes pod, or defining it, I should say, we that it should identify based on a specific service account. And what then happens in the background is that a token for that specific service account is going to be downloaded by the kubelet when the pod gets created somewhere. And then if the pod tries to connect to the Kubernetes API server, that token is then used as the API key, or let's say like the password for the service account. And then that way, now our application can talk to the API and can do stuff over there if that's something that we want to do. Finally, from the security point of view, network security. So networking in general is going to be next, but because we don't always, let me say it this way, not all of our traffic that happens on the Kubernetes cluster goes over the actual physical kind of network. You can understand that, like if two pods are on the same machine and they want to talk to each other, and then of course it makes sense that they do that directly without going over the network per se. Similarly, if two containers talk to each other inside a pod, that doesn't go anywhere either. So we need to have some kind of a way to limit that communication on a pod level. And that's what we define using network policies. These have now pretty recently been standardized, and we have multiple implementations of network policies. So there are different kinds of services that when actually then work kind of as firewalls in your Kubernetes cluster, implementing those network policies. But network policies are a standard object that allow us to define exactly the type of network that we want to, or the kind of network traffic that we want to allow or deny. Well, what kind of network traffic is there then? You could start off by just internal communication, right? So in Kubernetes, or in pods, different containers can talk to each other. If you've ever done a container yourself, then you know that usually you bind it to a particular port, right? So now if we have multiple containers in the same pod, then that means that on an operating system level, they are working in the same namespace, the same Linux namespace. And that means that they can talk to each other pretty freely. The standard way of talking to each other would be talking to the local host interface, so the IP address 127.0.0.1, and then the port of the container that you want to talk to, right? Pretty simple, doesn't take any much CPU, and tends to work. Basically, if the two containers share the same namespace, they could also do direct Unix socket communication. But that's normally not used. Normally, we just use TCP/IP over the local host port. Then if pods talk to each other, like I said, if two pods are on the same machine, then we do a local communication. So inside the same machine, they're usually these kind of virtual Ethernet devices, one for each pod. And they are mirrored on the pod side. So the pod talks to a virtual Ethernet device, and then that goes over to the host system. And then the kernel of the host system uses something like IP tables to then route the communication to the correct virtual Ethernet device for the receiving pod, right? And then the pod will see a virtual Ethernet device, and magically data will just start coming through that. If the pod is on a different machine, then the kernel will just, instead of sending that data to a virtual Ethernet device, send it to the actual Ethernet device, the one that the host operating system is using for network communication. And then hopefully that packet will be routed to the target machine that contains the pod that we want to talk to. It seems awfully difficult. You kind of need to know what the IP address of a pod is that you want to talk to. That sounds weird. It's not really good if we want to, especially if we want to do stuff like scale pods up and down. And yeah, what if a machine has gone down? So we need the pod to go somewhere else. And then, yeah, the IP address will change. Well, there's another way to talk to pods. And on Kubernetes, we call that a service. So a service is a kind of collection of pods. You could even say that it is there might be multiple copies of the same pod that are backing a service. And how do we now connect to those services? Well, they come in different implementations. Now, from a networking point of view, the most basic service is backed by something called a cluster IP. Cluster IP is a really Google style of doing things. It's like a bit of a hack, to be honest. So a cluster IP, or when we are creating a Kubernetes cluster, the Kubernetes API server as configuration needs to have an IP range that is not routable on your network. Okay? So let's say, if your network is on a 10.0.0.0 IP range, then the cluster IP should not be. Rather, it should be on something like 192.168.0, right? So why is that? Well, because we don't actually use the cluster IPs on the network at all. A cluster IP is a little bit like a DNS name for a service. So when we create a service that's backed by a cluster IP, a random IP is going to be used. Yeah, let's say 192.168.0.1. And then after that, when we talk to that service, we just talk to that IP. Now you're thinking like, no, Johannes, that doesn't make sense because you said that our internal network is a 10.0.0.0 network. So where would that traffic be routed to? Well, that's the whole point, right? So again, the host system kernel has something like IP tables on it, and that will then change the IP address of this of the cluster IP into one of the IP addresses where a pod is running where that service that is backing that service, right? So let's say we have two pods backing a service, and they are running on IP addresses 10.0.0.1 and 10.0.0.2. Now, if my pod wants to talk to a service, and then it connects to 192.168.0.1, that traffic goes out of the pod using the virtual Ethernet port, gets into the host operating system, and there IP table sees, this is one of those service IPs, and changes the to header of that datagram to say 10.0.0.1 or 10.0.0.2 before forwarding it onto the network. Okay. So we're kind of doing like DNS, except that we don't need to look up anything. We're just changing IP addresses. And now naturally, let's say that particular service decides to generate another pod, 10.0.0.9. Now all of the IP tables on all of the servers on our cluster will be updated, letting them know that this cluster IP now has actually 3 IP addresses that we can use for traffic. Okay, that's all good. But Johannes, if there is such an IP that's not routable on the network, then what if I want to talk to that service from outside of a Kubernetes pod? What if I have some other system that's running somewhere and it needs to talk to this service? It can't find it, right? Yeah, right. Okay, so let's do something else then. Let's create a node port. What is a node port? A node port is similar to a cluster IP, so that we have something that is unique for our service. But this time it's a port number. So again, when we create a Kubernetes cluster, besides defining this IP range that is non-routable, we also need to define a port range. We usually use fairly high non-root ports for this. Let's say we're going to use 30,000 to 31,000. That's our port range. So now our service is going to be registered, and we're going to tell Kubernetes to use a node port for it. And let's say that it's the first service, so it gets port 30,000. So now my application can, on the network, talk to any of the Kubernetes workers, so any server that is running our Kubernetes pods on port 30,000. Okay? And what that node does then, again, IP tables, it takes in the network traffic. It came in on port 30,000. It looks up, okay, which service does this belong to? And then it forwards that traffic to the cluster IP of that service. So let's say it was the same service, right? Traffic comes in on port 30,000. So we forward it to IP address 192.168.0.1, and then on the port that our container is running on. So we change the port as well. And then, of course, that doesn't work. So again, that gets changed into that 10.0.0.1 or 10.0.0.2 or 10.0.0.9 IP address before it gets thrown back onto the network. All right. So this way we can talk to a service from outside of the Kubernetes cluster. Then you're like, but what if I want to run a website? Then I need to select the port to be like 80 or 443, right? And what if I want to run multiple websites? So I have multiple different services that all want to have either port 80 or 443 or both, or whatever. What do we do then? Oh, okay. So then we need the load balancer, right? So the load balancer will terminate the traffic. It's outside of the Kubernetes cluster. It's just a load balancer. And then it will forward the traffic into the Kubernetes cluster using the node port of the service, right? So if service 1 gets traffic on port 443, the load balancer is going to terminate that traffic and then send that traffic or do a backend request on any IP address of the cluster on port 30,000. And then again, the operating system is going to receive that traffic, look up the service, change the port to be, for example, 80, change the IP address to be 192.168.0.1. And then the next step is again going to change the IP address to be 10.0.0.1 or 10.0.0.2 or 10.0.0.9. And then the traffic will actually end up in the correct pod from the outside. Besides load balancer, a load balancer very often in Kubernetes is like a fairly basic construct, something like an IP load balancer or network load balancer, so layer 4. We can also do layer 7 load balancers. However, they are often implemented as an object type called ingress controller in Kubernetes. It kind of depends on what kind of cloud environment you're in, like which one is the exact implementation. The idea with an ingress controller is that it works like a load balancer, but we can actually look at the GET request. So we can say that different services would implement different parts of a URL, for example. And then finally, we also have this idea of a service mesh, right? So in a service mesh, what we're doing is basically we're creating an overlay network where the mesh control layer knows about all of the physical locations of all of the services. And it's very similar to what we're doing, like with the cluster IP node port thingy. The cluster IP node port is a little bit of a hack, and it doesn't include any security controls. So with a service mesh, what we would do is we would deploy a sidecar container with all of the other containers that are part of that same mesh. And then whenever our application wants to talk to something, it talks via the mesh interface, so via that sidecar container. And then that sidecar container does stuff. Like, for example, it continuously updates so that it knows where all services are running. It can also do, for example, retries, or it can have a circuit breaker, like if it's trying to talk to a service on behalf of our application and it doesn't get a response, then it can tell the control layer that, hey, there's something wrong with this. Is this running somewhere else? Can we use a different copy of this service, or do we need to reboot it? And all of that kind of high-level activity, as well as, of course, now we can do security. Like if an application is not supposed to talk to a particular service, then the service mesh can enforce that because the application itself doesn't know how to talk to anything except for the service mesh itself. Service meshes have been a pretty effective pattern in the last couple of years. And there are multiple implementations of service meshes available. So with different kinds of functionalities, of course. And then onwards to our final topic, debugging and troubleshooting. When we are moving our application into a new environment, and then of course, different kinds of problems become a little bit more difficult to troubleshoot. We are kind of losing visibility as we are adding these abstraction layers into the kind of architecture. So from the application developer's point of view, we still use the same basic tools. So we still log stuff, and we're creating some metrics that we're sending somewhere. Logging can be done as simply as just writing to a specific file. And then very often what we're seeing is we are having some kind of logging frameworks that are then gathering all of the logs from all of the pods on a particular host and forwarding them to a centralized logging system. So for example, FluentD is a fairly popular log collection system. It runs as a pod itself on every host in a Kubernetes cluster. The Kubernetes cluster itself is also creating logs as well as metrics. Now, the metric system that gets used with Kubernetes most often is called Prometheus. And it's a little bit different from traditional metric systems in the way that Prometheus kind of thinks that services are publishing their metrics themselves, but the services are not sending them anywhere. You could think of there like being an HTTP request that will just, return back a particular metric, like how many users are logged in currently. That will be like one URL, and the application's job is to just publish that. Just whenever somebody requests that, then give back the number of users. And then Prometheus is the metrics collection server. So it iterates over all of its targets and calls these URLs and then saves the number that it got back. And that is the metric, right? So that way, we can, on the server side, decide like how often do we want to collect a new value, basically what our sampling rate of that metric should be. And we are in control. We can tune that up and down as quickly as we want, right? Because we don't have to change the application code to get like more nuanced views onto the metrics. For log collection, like I said, FluentBit is often used for log analytics. I think still ELK is kind of the way to go. So Elastic Search, and then L stood for Logstash, but that should be FluentBit now. And then K stands for Kibana, so as that kind of visualization layer. So that's definitely one thing. By the way, the visualization part of Prometheus is called Grafana. Okay, so that's kind of that tool set. Besides that, we can also do tracing. Tracing is if we have multiple services that need to talk to each other, tracing allows us to basically have a kind of a correlation ID follow those calls so that we can see how a particular use case has bounced between services and kind of where was it that something went wrong. There is a standard called open tracing for this, and I think the most popular implementation of that is something called Jaeger nowadays. It's originally by Uber. So Jaeger is a kind of a tracing implementation as well. What else? Conformance testing. Like when we are talking about Kubernetes clusters, kind of the one of the problems that we might have is we can do so many things. We can easily deploy lots of pods and have them talk to each other and use up CPU and memory and all of that. So kind of keeping track of all of that and making sure that it is still conformant, still according to the rules that you have set within your organization can be difficult. So there are also a couple of tools to do that. Sonovoy is one that could be used. And there is also this kind of certified Kubernetes conformant program that allows different kinds of distributions to prove that they are kind of the real deal. That like, for example, that their network policies are actually doing what they say, right? But yeah, that's kind of maybe a little bit too detailed for our interest. So before opening the floor for further questions, let me plug our upcoming course. So we are going to deliver the official Linux Foundation Kubernetes for Application Developers course for over 3 weeks, starting May 19th. So that's the Monday in 2 weeks, right? So 2 weeks and then the next weekend plus 2 weeks. This course is going to be handled every Monday, Wednesday, and Friday at 3 p.m. for 2 hours each. It's the official Linux Foundation course, so you will get the materials sent to you as a printed book, hopefully before the start of the course. And there is a labs environment included, as well as a lot of the content is actually hands-on labs with, step-by-step instructions. All of the meetings will be recorded, however, audio only, as Linux Foundation doesn't allow us to distribute the slides in video format. We can only do live video. And then, of course, when we do labs in the meetings, then those will be in video format, not only audio. If you pass this course, there's going to be an official Linux Foundation badge in Credly that you will get. And then, of course, you should also be ready to take the Certified Linux Developer Associate exam. We can also sell a voucher for that for you with a discounted price if you are interested. There is a really complicated code here for getting 40% off the normal price of our course. However, the QR code on this slide should also work. And you're also going to get spammed by Maven with that code, I guess, in a couple of days. So if you're interested, just wait a couple of days until you get the email or let us know, and we're going to send that code to you. With that, let's open up the floor if there are any questions. In case there are not any questions, then feel free to email me at johannes@deepdives-eu. I'll put that over into the chat. And then that's chat. That's the email. So if there are any questions later on, let us know. Thank you wholeheartedly for listening through these 45 minutes. And Good luck with your endeavors as a Kubernetes developer. Hope I see you in a couple of weeks. Till then.